Welcome back to R for Economics, and we're just going to go through some of the special matrix functions operators that are in R. So let's just generate some vectors. So X and B, little b will be vectors, A will be a matrix, B will be a matrix, and then C we'll get by just doing the product of these two, B and B transpose. So this is the transpose operator, B transpose B. Okay, so element-wise means that the first, the one in the top right, we look at A mat A, it'll multiply 1 times 1, or and 4 times 4, and we can see this when we run this. Okay, so it's taking each element and it's multiplying it by itself. So this is element-wise multiplication. Matrix multiplication does the proper matrix multiplication. You can see that these two things are going to be different. Even if we did A times A, that should be an uppercase A, they're not conformable, so we'd actually have to do transpose. And this is the important part. Note that it gives you a different value than what you got here. Okay, because it needs to be transposed, they need to be the same dimensions. Notice that this is 3 by 4. Okay, so you have to be careful when you're multiplying your matrix. The outer product is going to give you, is from the percent O, and that's an O, not a 0%, and that will give you a lot of output doing the outer product. Cross product will be is A time, sorry, this would be like B times A prime, and then this one would be like A transpose. Okay, so the prime is just giving me a transpose, and you can see that it gives me the cross product. Note that this cross product and this one up here are the same. All right, now we've got a transpose, simple operator. So if we look at B mat, we can see that it's now transposed. The 11 is where the 17 is, and the 17 is where this. When you do a diagonal of a vector, it will just be the 1, because the x vect it simply goes down the main diagonal. Okay, now if we had an R vector, so let's say we had, let's see what happens if, so B mat is just going to take the diagonal of B. So if I do a diagonal of 1, 2, 3, note that if you give it an R vector, it's going to actually just put those along the diagonal. Okay, so anything that's a matrix, it will maintain that matrix and just grab the diagonal, the main diagonal. So 1, 9, 15, and 9. This one, it says 1, 2, 3, put them on the diagonal. If we diagonal a number, an actual integer, we get an identity matrix of that size. Now, the other one is an inverse. Now, we usually use a solve command, which solves y is equal to inverse of B mat times x. Okay, so that's solving that. And if we just want to get the inverse, we just have to give it the actual matrix. Now that matrix has to have certain properties. It has to be invertible, and we can see that this is the inverse of B mat. Eigenvalues and eigenvectors. Notice that you can obtain the $sign values, $sign vectors from this one. if you want the Chaleski decomposition, the importance of the Chaleski decomposition is that the D times D will actually return its original, D transpose D will actually give it back the original matrix that you gave it. Singular value decomposition will give you the DUV. QR will also give you a different type of decomposition. And you can extract these just by using the $, whatever it is at the end. $, D will give you just the D vector back in return. The other things you can use are row sums, row means. So you can obtain those quite easily. And if you want them to be a matrix, just simply that, or as matrix will also give you a matrix. There's also is matrix, which says is.matrix and a.mat. And yes, it's true. If I go is.matrix and give it 1:13, it says false. Okay, so these are just operators that you can use. There are a few more, and in fact, there are packages that you could download, and they'd give you even more capabilities as well. Great, and we'll see you in the next video.